Very good morning to all the participants. Uh, Welcome to the third day of the GAN course on the automotive emissions control and scopes of alternative green fuels. Today, our first lecture will be lecture 7 on future outlook on emission norms, standard test conditions, and engine cycles. So I welcome Professor Wen Man Ming from NUS and over to you, sir, for the next particular lecture. Thank you, sir.
Okay, thank you. Okay, very good morning to everyone. Today we're going to introduce various emission control standards. Actually, you guys still maybe you guys still remember yesterday we had introduced the long history of smog in various countries, especially in some major countries like UK, USA, China, India. Actually, similar cases also occur in other major countries like Japan, Germany, correct? As a result, okay, to control the emissions from transportation system. So various emission standards has been set since then. So today we're going to introduce the major emission standards, which is commonly used by the major countries. Okay, so today actually we are focused on the Europe emission standards because this emission standards actually is commonly used by the all the major countries. And so this one also is a representative of the emission standards, okay? Okay, so the first emission standards was set in 1992. In 1992, okay, so this one is a Euro 1. The introduction for Euro 1 standards actually was a revolutionary step and had a significant impact on the air cleaning for the air pollution for the world. Okay, so here we show you the history of Euro emission standards. Firstly, in July 1992, Euro 1 was set. And at beginning, we can say actually the major emissions value is still very high. For example, CO emissions is set to be 2.72 grams per kilometer. And HC plus NOx emissions, case overall emissions should be lesser than 0.971, and the PM is 0.14 grams per kilometer. Okay, then starting from 1996, the Euro 2 was set, and compared with Euro 1, we can see CO emissions has been reduced by more than 60%. And the HC and NOx emissions has been reduced by more than 20%, and the PM also has been reduced by almost 50%, right? Reduced from 0.14 to 0.08, okay, close to 50%. Then in 2000, Euro 3 was adopted. Okay, so the CO emissions has been further reduced from 1 grams per kilometer to 0.66 grams per kilometer. And at the same time, starting from 2000, NOx emissions also is under control. Before that, actually there's no limitations on the NOx emission for the passenger cars, okay? Then, okay, so total value for HC and the NOx emissions has been dropped to 0.56 grams. Then, starting from 2005, Euro 4 took effect, and the CO emissions has further dropped to 0.5 grams per kilometer. Then, since then, okay, there's no adjustment anymore for CO emissions. However, NOx emissions continue drop. Okay, for example, Euro 4 dropped from 0.5 to 0.25. Okay, so dropped by 50%. Say Euro 5, okay, this value has been further decreased from 0.25 to 0.18 grams per kilometers. Euro 6 also further decreased to 0.08 grams per kilometer. So it's a big drop, correct? Drop more than 60%, okay, from Euro 5 to Euro 6. And also the HC and NOx emissions also has been decreased by about 30%, okay? And the PM emissions actually says no further adjustment from 5 to 6, okay? From 5 to 6. And okay, one point we should pay attention to is starting from Euro 5, the particulate numbers also has been taken under control. Okay, so the total number, the particle, okay, the subparticle numbers should be less than 6 times 10 positive 11 numbers per kilometer. Okay, so this one is for diesel engines, okay, for diesel car. For petrol car, we can say actually Euro 1 is the same. For CO emissions, it's 2.72 grams per kilometer. And then Euro 2 dropped to 2.2. Euro 3 actually increased a little bit from 2.2, increased to 2.3. However, starting from Euro 4, okay, this CO emissions has been reduced to 1 grams per kilometer. So we can see for the gasoline engines, okay, the total hydrocarbons also has been put under consideration. For example, so in Euro 3, the limitations for the total hydrocarbons is 0.2 grams per kilometer. Then Euro 4 further dropped to 0.1 grams per kilometer, correct? And okay, this is MHC is a non-methane hydrocarbons. Okay, so this one was limited to 0.068, starting from Euro 5. Okay, starting from Euro 5. So for NOx emission, so you can see the NOx emission is 0.06 for Euro 5. So if we compare the NOx emission for diesel car and the gasoline car, so you can see the need for diesel car, the limitation for NOx emission is higher than that for gasoline car, correct? Actually, yesterday we have introduced diesel engines has a higher peak temperature, higher pressure. As a result, the NOx emission produced by diesel engines will be higher than that of our gasoline engines. That's why the limitation also will be different. Okay, the limitation will be different for diesel engines and the gasoline engines. Okay, if we compare the PM, the subparticles, actually we can see at beginning, there's no limitation for gasoline engines because we have mentioned at beginning, correct? Gasoline engines, actually the main emissions is CO and HC. However, for diesel engines, the main emissions is NOx emission and the subparticle emissions, correct? So we can say at beginning, there's no limitation for the gasoline engines. However, for diesel engines, we have set the target, set the limitation for subparticles is 0.14 grams, correct? Then gradually drop to 0.0045. Then for gasoline engines, okay, starting from Euro 5, okay, we also has the limitations. Okay, the band is 0.005. Okay, this band is the same as diesel engines. Okay, it's the same as diesel engines in terms of grams per kilometer, and also in terms of number concentrations. Okay, so it's the same. Okay, so for this graph, actually, you cannot see how much we have reduced the major emissions. Okay, but based on this graph, we can easily understand how much reduction on the upper limitations for the major emissions. For example, for NOx emission, so you can see Euro 1 is 0. Okay, the NOx emission is 0.78, correct? 0.78. Then for Euro 5, Euro 2 dropped to 0.7, Euro 3 dropped to 0.5, Euro 4 dropped to 0.25, and Euro 5 dropped to 0.2, correct? Euro 6 dropped to 0.1, correct? So we can see this is a very significant drop on the upper limit, okay, for the NOx emission as well as for the PM emissions, correct? So we can see at beginning, Euro 1 is 0.14 grams per kilometer. However, by Euro 5, okay, this value has dropped to, has been decreased by more than 95% already. Okay, has been decreased by more than 95%. So that's a big drop on the upper limit. Okay, on the upper limit for the major emissions. Okay, this one for diesel engines, for diesel cars. And for gasoline engines, okay, actually quite similar. However, for gasoline engines, gasoline cars, actually before Euro 5, okay, there's no limitations on the PM or subparticles, correct? However, start from Euro 5, okay, we can see the limitations is similar to the diesel engines. Okay, so similar to the diesel engines, it's very small. Okay, just now we introduced the Europe's emission standard for the passenger cars. Okay, now we're going to introduce the emission standards for light vehicles. Okay, light vehicles. So Euro 1 actually you can see it's similar. It's the same. Okay, it's 2.72 for CO emissions, correct? It is the same as passenger cars. Okay, we should be careful. Since the light vehicles, the weight should be lesser than, the mass should be lesser than 1,305 grams, kilograms. Okay, so it's a very small light duty vehicles. And start from Euro 2, the CO emissions drop to 1.0 grams per kilometer. And then Euro 5, okay, drop to 0.5. After that, there's no further adjustment of CO emissions. For NOx emission, starting from Euro 3, we had limitations for the net duty vehicles. Okay, from Euro 3, so the upper limit for NOx emission is 0.5, then gradually drop to 0.18 grams per kilometer. HC and the NOx emission, this value also has been dropped from 0.97 to 0.17 gradually, correct? Also has the PM limitations. Okay, so a final value for starting from Euro 5 is the same as a passenger cars, okay, 0.0045. And the subparticle numbers also is the same as passenger cars, correct? For gasoline engines, okay, for this one is for gasoline engines, then the CO emissions has a higher limitation. For example, Euro 5, we can see CO emissions, the upper limit is 1 grams per kilometer. And this is for diesel engine, CO is not a major emissions, so has more strict limitations on CO emissions for diesel car, correct? And okay, so total hydrocarbons, okay, we start from Euro 3, we set the value is 0.2, because just like I mentioned, for gasoline engines, HC also is a major emissions for gasoline engines. And start from Euro 4, okay, the value drop to 0.1. After that, there's no further adjustment. Okay, this one is for the NOx emission. Also only start from 2000. Okay, then we have set the target is 0.15 grams per kilometer. Then gradually drop to 0.06. Okay, starting from Euro 5 since 2009. And also for the PM, only start from Euro 5, we had limitations on the PM, on the emissions for gasoline engines. Okay, so next one is the Europe emission standards for heavy-duty vehicles. So we can see the value is much higher, okay, much higher than that for the net duty vehicles, correct? So can see CO emissions start from 4.5 euro 1, okay, start from 4.5 grams per kilowatt hour. Then euro 2 drop to 4.0. Okay, that's only a net adjustment, correct? HC, there's no change from euro 1 to euro 2. And NOx emission only drop from 8 grams per kilowatt hour to 7, also only a net adjustment. However, starting from euro 3, so can say it's a big drop. Okay, for example, CO emissions drop from 4.0 to 2.1. Okay, 4.0 to 2.1. Then euro 4 further drop to 1.5. Okay, euro 5. Euro 6 also is 1.5. There's no further change anymore. And HC initial value is 1.1. Then again, start from euro 3. Okay, start from euro 3 is the value drop to 0.66 grams per kilowatt hour. And then euro 4, euro 5, okay, drop to 0.46. Drop to 0.46. And starting from euro 6, starting from 2012 December, so the value will be further drop to 0.4. Okay, drop to 0.4. And the force HC drop to 0.13. Okay, so that's a big decrease on the upper limit for the HC NOx emission, correct? And also here shows the PM evolution. So at beginning, case limitation is 0.61 2 grams per kilowatt hour. Then euro 2 drop to 0.25, euro 3 drop to 0.02, and euro 4 drop to 0.02. Okay, euro 6 drop to 0.01. So again, case value you can see from here to here. You can see actually has dropped by more than 98%, correct? Okay, smoke. Yeah, interestingly, we can look at the smoke emissions. Before Euro 3, okay, there's no upper limitations on the smoke. Start in 1999, so has limitations for smoke is 0.15. And then, okay, this one, okay, 0.8. Okay, this one is supposedly enhanced vehicles, which means in this kind of vehicles actually has been made cleaner. Okay, so for the normal vehicles, okay, actually it's this value 0.8. Okay, 0.8. And then start from 0.5 drop to 0, start from euro 5 drop to 0.5. Okay, drop to 0.5. After that, there's no further adjustment. Okay, and actually interestingly, we notice that from start from euro 6, okay, there's no limitation anymore. Okay, so I have one question for you guys. When start from euro 6, we remove the smoke control, so there's a emission standard. Why there's no emission control for the smoke in Euro 6? Anyone knows? You can guess. Why start from Euro 6? There's no emission standards or limitations for the smoke.
Sir, I think the new engines won't produce smoke.
Okay, yeah. Okay, so for the new engines, the engines build more and more advanced, correct? So because of the advancement of technology, okay, since we can meet the regulations for HC, CO, NOx, and PM under such a small value, there's definitely no problem for the car to meet the smoke emission standard. Okay, that's why it removes the smoke. Okay, if we have smoke, for example, still equals to 0.5, then you cannot achieve this value. It's impossible to achieve this value. Okay, that's why the removes the limitation for smoke because it's impossible. Okay, so next one is the emission standards for motorcycle. So you can see it's very much higher than the passenger cars, than the light duty vehicles, even more than the heavy duty vehicles, correct? Why? You can see it's very sturdy, correct? For the passenger cars is only 2.72, correct? So this one is much higher. So why the limitation? Okay, the limitation for the motorcycle is higher than the passenger car, than the light duty vehicles. Anyone knows?
Gasoline engines.
Okay, yeah, because of the motorcycle, the engine is a small engine. As we know, the smaller the engine, usually the lower the efficiency, correct? And also for the motorcycle, actually most of the engines are two-stroke engines. Two-stroke engines usually has lower efficiency and higher emissions. Okay, lower efficiency and higher emissions. Okay, because for two-stroke engines, the power stroke is shorter than the four-stroke engines, correct? As a result, the duration or the time for combustion process has been reduced. Okay, so the CO emissions will be higher than that for the four-stroke engines. Okay, yeah, the major issue, okay, is for the small engine. For the motorcycle engines, too small. Okay, too small. So the time for combustion process is too short. Okay, so CO emissions is much higher compared with the passenger cars and the light duty vehicles. And however, okay, with the advancement, so you can see from Euro 1 to Euro 2, okay, the CO emissions has been cut by more than about 60%, correct? Start from Euro 2 to Euro 3 also has been further cut by 60%. Then to Euro 4 dropped to 1.14, and Euro 5 is 1. Okay, this one is the same as the passenger cars already, correct? Okay, then for the LOX emission, is the initial value is 0.3 grams. Actually, it's more than the passenger cars. Okay, again, because combustion process is poor than the passenger cars. Okay, thereby the LOX emission is lower. Correct? Because the combustion process is poor, which means that the peak temperature will be lower and the NOx emissions will decrease. Okay, so for motorcycle, NOx emission actually is lower than that of passenger cars. At the same time, actually, have you noticed this one? This unit is grams per kilometer. Grams per kilometer. Okay, so motorcycle is lighter than passenger cars, correct? Motorcycle basically is only maybe 50 kg or 100 kg, correct? But the passenger cars can be easily 600 kg or more than 1,000 kg, correct? So in terms of if you change into the same mass, okay, change into same size, then okay, the NOx emission still higher for motorcycle, correct? And HFC emissions also is higher for the motorcycle. Also are due to the combustion process is poor than the passenger car, okay, than the big engines. And the PM and the CC emissions is the same as passenger cars, and HC emissions also is similar. Okay, the next one I want to introduce is the India norms timeline. Actually, the India, the emission standards is quite similar to the Euro norms. Okay, the band is almost the same. It's almost the same. That's why we focus on the Square Europe emission standards. Okay. So this one is shows the timeline for the whole country, for the whole India country. So you can see the BS3, okay, the stage 3 emission standard start from 2015, and then since 2017 has been replaced by the BS5 for the nationwide. And start from 2020, the second quarter, gets the stage 6 took effect. Stage 6 took effect. And for the 13 major cities, okay, from 2015 to 2020, so you can see the BS4 took effect. Then start from 2020 second quarter, the BS6 took effect. Okay. So here shows the major emissions limitation. So you can see this value actually is the same as Euro emission standards, correct? So this one is the BS6, okay, it's the same as the Euro 6, right? For example, CO emissions is 1 for gasoline engines. For diesel engines, 0.5, okay, it's the same, correct? HC is 0.1 for gasoline engines. NOx emission 0.06 for gasoline engines and 0.08 for diesel engines. These are all this value actually is the same as the Euro 6, correct? Okay, the next part I'm going to introduce the vehicles test cycles. Okay, the vehicle test cycles. By using this test cycles, actually you can find out the emissions produced by the vehicles under simulated conditions or which is close to the city or urban traffic conditions. Okay. So here I want to introduce what's harmonized net duty test cycles or WLTC. So you can see the test actually consists of 4 processes. Okay, so first one is no speed conditions, correct? No speed conditions. So you can see the okay. So here show you the maximum speed is 56.3 kilometer per hour, and the running time is 589 seconds, and the stop time is 156. Okay, 156. So you can see here shows the variation of the speed during the test. So we have some duration here from here to here. This part actually is the car stop, and here also the car stop. Okay, that's why for the testing duration is 589, but also we have 156 is the car will stop. Okay, so this one is simulate the traffic in the city, correct? Because in the city, okay, because the traffic light, sometimes you have to stop and wait for the traffic light, correct? And so total distance walked by the car will be 3,095 meters, and the stop timing percentage is 26.5. Okay, this one is use 156 divided by 589, so we can get this ratio. Okay, so second stage is the media speed. Okay, media speed, the maximum speed is 76.6 kilometer per hour, and the running time is 433 seconds. Okay, so this one is the second stage, media speed. Then the third stage is high speed. So the running time is 455 seconds. Okay, and the last one is the extra high speed. This one actually is higher than the rated speed. Okay, so under conditions, the maximum speed is 131. Maximum speed is 131.3 kilometer per hour. Okay. Okay, so here shows the average speed. Okay. For example, in the first stage, the average speed is 25.7 kilometer per hour. For the media speed, the average speed is 44.5, and third stage is 60.8. Fourth stage is 94 kilometer per hour. Okay, so this duration is 25.7 average speed. This part is 44.5. Okay, this part is 60.8, and this part is 94. The average speed. Okay, but we know in the test actually the test machine was next. Okay, the traffic the speed is not constant. Okay, so you can see the speed is always change, correct? With time, it's always change, correct? So under the conditions, you can measure the emissions produced by the vehicle. Okay, this one can be after obtaining the results, we can see whether can meet the emission the car emission standards. Okay, so also had class 3B and class 3A. Class 3B is the maximum speed greater than 120 km/h, and class 3A, okay, the maximum speed should be less than 120 km/h. But the total testing duration is the same, 1,800 seconds. And the stop duration also is quite similar. It's the same. The distance watched by the car will be a slightly different. Okay, slightly different. Okay. Okay, the next one I want to introduce is the worldwide harmless net vehicles test cycles. Okay, so we have 3 classes. We have 3 different classes. Okay, this is 3 classes. Actually, is based on this called power to mass ratio. Okay, power to mass ratio. So let me write. Okay, power to mass ratio. Okay, so if the power to mass ratio is less than 22, then it's class 1. Okay, if the power to mass ratio is more than 22 but less than 34, then it's a class 2. When the power to mass ratio greater than 34, then it's a class 3. Okay, so class 3 means it's more powerful, and the class 1 is the least powerful engine or vehicles. Okay, so for class 1, so you can see for class 1, we only test the speed from lower speed to medium speed, correct? Then we finish the testing. So the total testing duration is only about 1,000, okay? Only about 1,000 seconds, correct? Then for the class 2, we test until this position is a high speed. Okay, test until the high speed. Okay, so the total test time is about 1,400 something. Okay, 1,496. Okay, then for the class 3, we test a very high speed also. Very high speed also. So the total time is 1,800 seconds. Okay, 1,800 seconds. Okay, so here this one shows the speed variation for the 3 types of vehicles, light duty vehicles. Okay, and here show you the acceleration versus the time. Okay, the acceleration versus time. So you can see the maximum value for the class 1 is the smallest, correct? Because the class 1 is the least powerful vehicles, correct? Yeah, so the acceleration cannot be too high, correct? Which is followed by the second class. Second class, actually, the acceleration is higher than the first one, but lower than the class 3. Okay, the class 3 has the biggest acceleration, right? Has the biggest acceleration. And okay, class 1 only tests from 0 to 900 to 1,000. Okay, to 1,000 seconds. The second class tests from 0 to 1,400 something, correct? And the class 3 tests for the whole range. Okay, this one is the India drive cycle. India drive cycle actually is quite similar to the new European driving cycle. It's quite similar, correct? Okay, so this one is the modified India operating cycle. Okay, India drive cycle, and it is the same as Europe driving cycle until this position. Only at the extremely high speed. Okay, there's a slight difference between the India multi-phase India drive cycle and the European drive cycle, correct? Only a bit difference here. But the earlier stage, the India drive cycle actually only test only test until the media speed. Okay, and the test duration also is shorter than the IDC, and also shorter than NEDC, correct? So this is a multi-phase India drive cycle actually can cover a wider range, speed range. Okay, wider speed range. Okay, so it's more practical. Okay, so next one I want to introduce is what harmonized stationary cycle. So this one is also called the 30 operating conditions testing cycle. So had 30 different operating conditions, okay, with a different speed and a different engine load. For example, so first one is idling conditions. Okay, idling conditions, so the speed is 0, correct? And the engine load is 0, correct? Second condition is 50%, 55% of the rated engine speed. Then the engine load is 100%. Okay, so second case the same speed, but the engine load dropped to 25. The third one dropped to 70. Okay, drop to 70, correct? And the second case, to the fourth case. Then for the fifth case, the speed dropped to 35%, and the engine noise is 100%. Okay, so can change the speed and also change the notes. Then measure the measure of course the testing time also is not different. It's not the same. Okay, it's not the same. For example, idling conditions is 210 seconds, and the second case is 50 seconds, and the third case is 250 seconds. Okay, so for the different conditions, different case, the testing time will be different. But the total time is 1,895. Okay, this method, this stationary cycle is commonly used by all kinds of countries. Okay, by all kinds of countries. Okay, so the next one is what harmonized transit cycle. Just like is a stationary cycle. So once the car reaches this operating conditions, for example, 55% of speed and 100% loads. Okay, then we'll keep this parameters constant and run for 50 seconds. Okay, so this one is a stationary operating cycle. However, this one is a transit operating cycle. So we can see the speed. Okay, this one is the torque, and this one is the speed. So we can see the torque is always changed, it's not constant, right? During the process, okay, at different timing, the torque will be different, and also the speed also is a change only as a position in this duration. The engine speed is almost the same. It's almost the same. But even the engine speed is the same, however, the torque is still change, correct? The torque is still change. Okay, so this one is called the transit cycle. Okay, transit cycle. Okay, so the next one is what harmonized vehicle cycle. So this one actually is divided into three parts. Okay, so first one, the testing distance is 5.3 kilometer. Second one is 5.8 kilometers. The third one is 8.9 kilometers. Okay, so these three parts simulate different environments. Okay, for example, the first part simulates the urban area. Okay, so in the urban traffic, we know firstly the vehicle speed will be low, correct? Because we have a lot of traffic light, correct? And we have crossroads and the traffic lights. So also will limit the vehicle speed, correct? So for the first one is urban area, so urban environment. Okay, so the total time, okay, simulated time, running time will be 900 seconds. Okay, the second part is rural, simulate the rural area is 5.8 kilometer. And the time, running time is about from 900 seconds to this position. Okay, this position is roughly 1,350 roughly now, okay? So compared with the urban area, you can see the average speed is increased, is higher. However, it's still not too high, correct? Okay, so still not too high because the roads, okay, the road conditions is not so good in rural area. Okay, then the last part, okay, so the part simulates the motorway or the expressway highway. Okay, so in the highway, the speed is much higher, correct? It's the highest because yeah, the traffic is much better. Okay, the traffic conditions is much better. Okay. Okay, so in the third part, okay, the time, the running time is from 1,350 to about 80,000, to 8,000, okay, 8,000. Okay, so here show you the maximum speed for the urban area. Okay, roughly is about 66.2 kilometer per hour. And for the rural area, okay, the maximum speed is 75.9, but the average speed is higher than the urban area, correct? And in the highway, the maximum speed is 87.8 kilometer per hour, and average speed also is much higher than the urban area and the rural area. Okay. Okay, so last part for this lecture, I want to share with you is the basic principle for measuring the brake power, measuring the torque delivered by the engine. Of course, this one is just a introduced theory. Actually, this one is not used anymore because we use more advanced technology. For example, with hadronic power plant, not power plant, sorry, hadronic testing beds to test the power delivered by the big engines, especially by marine engines. Okay, and we can use the eddy current dynamometer to measure the power delivered by the normal engines, okay, by the normal diesel engines or gasoline engines, okay. But the principle is the same, okay. The principle is the same based on the moment balance equation, okay, moment balance equation. Okay, so here we show you the basic principle for this kind of measurement. Okay, so basic simplest one, okay, this meter is actually is used in the earliest stage, okay. So this one is the flywheel, and the flywheel is attached on the crankshaft, correct? Okay, then we use a friction band attached on the surface of the flywheel. Okay, so this one is a friction band, and this is a flywheel, and this one is the shaft, okay, crankshaft. Okay, so use a friction band to attach on the flywheel, and as we tightening this friction band, so a bigger friction force will be applied on the flywheel, correct? Okay, because we know when the engine is running, the crankshaft will deliver a torque, correct? Will deliver a torque. So if there's no any opposite torque to counter the rotation of the crankshaft, then what happens? The crankshaft will running faster and faster, correct? Okay, so we use this an anti-torque to counter the rotation of the crankshaft. Okay, so when these two torque are equal and opposite, then the engine will keep balance, correct? Then the engine speed will be kept as constant. Okay, so under these conditions, you measure the torque. Okay, you measure the torque delivered by the engine, by the crankshaft. Then we can know how much torque is delivered by the engine, and how much power we can calculate based on the torque. We can find out the brake power delivered by the engine, correct? So when this opposite torque is equal to the torque delivered by the crankshaft by the engine, okay, then we measure the opposite torque, then we know how much torque is delivered by the engine, correct? Okay, so firstly, we introduce the work done in one revolution. Okay, so the work done in one revolution equals to the distance times the force, correct? The distance times the force. Okay, so for one revolution, okay, this crankshaft and this is a flywheel will rotate for one circle, correct? So the distance worked by the friction force equals to 2 pi r. Okay, 2 pi r is perimeter, right? And the 2 pi r times the friction force. Okay, so this one is the work done by the crankshaft. Okay, the work done by the crankshaft. Okay, so we have 2 pi r times F, correct? And again, because this is a measuring machine actually produce the same torque and counters the rotation of the crankshaft, correct? So this torque should be equal to, okay, should be equal to the torque delivered by the engine, correct? So I've guessed the torque delivered by the engine, and the capital RF is the torque delivered by this weighing machine, correct? So these two should be equal and opposite, okay? Then the engine will be kept as constant. Okay, so we can find out the torque should be equal. So we have RF equals capital RF. Okay, capital R is the arm length, F is the force in measured. Okay, so F times arm length is the torque, correct? So moment. Okay, so has this T, the torque equals to RF and equals capital RF also. Thereby, okay, since work done in one revolution by the frictional force and by the engine, is 2 pi RF. Also, so the work done it also can be changed into 2 pi times capital RF, correct? And this one is work done in one revolution, correct? As we know, the engine speed is n. The engine speed is n, correct? So we use work done in one revolution divided by the time for one cycle, for one revolution. Then we can find out the power, because the power is work done per unit time, right? So work done per unit time, correct? Okay, so we can use work done in one revolution divided by the time for one revolution. Thereby we can find out the power. Okay, the power is the work done per unit time per second. Okay, per second. Okay, so the time for one revolution is 16 divided by n, correct? Because we know the engine speed. Because we know the engine speed is RPM, correct? And it is a revolution per minute. Okay, so this one divided by 16 become revolution per second. Okay, revolution per second. Okay, revolutions RP seconds. Revolution per second, correct? So for one revolution is 1 over RPS. Okay, set by equals to 60 over n. That's why we have this equation. Okay. So the brake power equals to this one divided by 1000. We change the unit from watts. Okay, in this case, the unit is watt. And we divide by 1000, then we can change the power to kilowatts. Okay, because watt is too small. This unit is too small. So we change the brake power to kilowatts. Okay. Okay, so yeah, we have finished this this lectures. Any questions?
Yes, from participants, if there are any query, you can ask Professor.
Okay, start from next class. We are introduce alternative fuel, and also we are going to introduce, of course, the latest design on the ammonia marine engines. Okay, so we introduce a new concept. We can achieve net zero greenhouse gas emissions. Okay, yeah, but next class we are going to introduce the alternative fuel, and then in the afternoon we introduce the marine engines. Okay, net zero greenhouse gas emissions marine engine, the next generation marine engines. Okay. So yeah, if no questions, we'll stop here. 10 minutes later, we
Yeah.
come back. Yeah, to introduce the alternative fuel. Okay.
Okay, sir. Thank you, sir,
Yeah.
for this
Okay. Thank
presentation.
you.